Stack refers to the area of an internal RAM which is used to store and return data quickly. It is an 8-bit register which is used by 8051 to hold an internal RAM address called as top of the stack. The address in the stack pointer register is the location in the internal RAM where the last byte of data was stored due to a stack operation. Whenever data is to be placed on the stack pointer increments before storing the data on the stack so that the stack grows up as the data is getting stored. Whereas when the data is retrieved from the stack, the byte is read from the stack and then the stack pointer decrements to point to the data which is available for next to be retrieved. 8051 has an internal RAM for data storage that can be altered by the program and ROM for program code bytes. Additional memory can also be added externally with the help of memory decoding circuits. 8051 uses Harvard architecture, so as a result you have same address in different memories for code as well as data. Internal circuitry access the correct memory based on the nature of operation which is in internal RAM. It is 32 bytes from the address 00H to 1FH, which forms the 32 working registers organized as 4 banks of 8 registers each. The 4 register banks are numbered 0 to 3 and each of the register is made up of 8 registers named as R0 to R7. Each register can be addressed by name or by its RAM address. Like say for example R0 of bank 3, if R0 from bank 3 is selected in PSW, else 18H whether bank 3 is selected or not. Register banks can be selected using the bits RS0 and RS1 in the program status word register. If the banks are not selected, then they can be used as general purpose RAM and bank 0 is always selected on reset. A bit addressable area of 16 bytes occupies RAM byte addresses 20H to 2FH, forming a total of 128 addressable bits. An addressable bit can be specified by its bit address from 00H to 7FH, or 8 bits may form any byte address from 20H to 2FH. A general purpose RAM area above the bit area from 30H to 7FH addressable are addressed as bytes. So whatever I said in the previous slide is shown over here diagrammatically. You have 00H to 1FH where there are 4 bank registers, 20H to 2FH which are bit addressable as well as byte addressable memory locations. 30H and to 7FH is used as general purpose RAM. Internal ROM. The internal program code present in ROM occupies an address space from 000H to 0FFFH. The program counter is used to address the program code bytes from the address 0000H to FFFFH. Program addresses which are higher than 0FFFH will cause 8051 to automatically fetch code bytes from external memory. Code bytes can also be fetched from an external memory addresses by connecting the external access EA bar pin to ground. Code bytes can be in internal ROM as well as in external ROM. Next, let us study about the I/O ports. The function of a pin at any given instant of time depends what is physically connected to it and what is the software commands used to program that particular pin. Both these factors are under the control of a 8051 programmer. 8051 has 32 I/O pins which are divided into 4 ports, namely port 0, port 1, port 2 and port 3. These I/O pins help 8051 to monitor and also control other devices. Each port consists of a D-latch, an output driver and an input buffer. All the ports can be defined as input or as output. Diagram shows how exactly a output port is being defined. All the bits are connected to data bus in the port register. When data is returned to port register, data bit is latched to D flip-flop in the port circuit. When the processor gives WR bar signal, that is the write signal, which is connected to an active low clock of the D flip-flop. The data from the data bus will be latched to the D flip-flop. If input is 0, D is equal to 0, then Q is equal to 0, Q bar is equal to 1, which turns T2 on. And since T2 is connected to ground, output will be 0. If input is 1, that is D is equal to 1, then Q is equal to 1, Q bar is equal to 0. T2 will be turned off and T1 is turned on. Therefore, you find output is equal to 1. While reading ports, there are two possibilities. First one is you can read the input pin. To define any port of 8051 as input, first you need to write 1 to the port bit. As a result, Q is equal to 1 and Q bar is equal to 0. In port 0 and 1, Q bar is connected to T2. In port 2, Q is connected to T2 through a NOT gate, and in port 3, Q is connected to T2 through a NAND gate. This you can see it in the next slide. In all cases, T2 is off pin is simply pulled high by the pull-up resistors and connected to input buffer. B2 is activated. Reading the latch, the other method. B1 is activated and data from Q is put to B1 buffer. So diagram shows all the 4 port pin structure: port 0, port 1, port 2 and port 3. Port 0 can be used as input, output and as an address and data bus to external memory. Port 1, they have no dual functions. They behave as simple input and output ports. Port 2 may be used as input or output port, and also it is used to send higher order address byte. Port 3 can be used as input and output port similar to port 1. The input and output functions can be programmed under the control of P3 latches or the control of other SFRs. Each pin of port 3 can also be individually programmed to be used either as IO or some other alternate functions. So the alternate functions are listed out in this particular table, where P3.0 and P3.1 are used for serial communication to receive and transmit. P3.2 and P3.3 are used as external interrupt resources. P3.4 and P3.5 are used as two timer or a counter. P3.6 and P3.7 is used for giving write and read signal for external data.